Welcome to your quiet corner of cosmic discovery. I'm here to share something genuinely fascinating about our universe at just the right volume for drifting off. You know what's fascinating? I've been thinking about this strange mirror world of particles called antimatter. It's like the shadow version of everything we see around us, but somehow it's incredibly rare. There's something remarkable about how the universe keeps almost all of it hidden. And I can't wait to share why that might be true and what it tells us about the cosmos. Should you find solace in these cosmic lullabies, consider becoming a regular dreamer by subscribing. Share what topics intrigue your curious mind in the comments below. First, let's create the perfect space for learning. Cocoon yourself in comfort, release any lingering tension, and let your breath become soft and steady. Beneath the surface of the everyday, hidden in the shadows of our familiar reality, there lies a secret so profound that it has both haunted and inspired physicists, writers, and dreamers for generations. It is the secret of antimatter, a whisper of the universe's symmetry, a reflection in a cosmic mirror that seems at once perfectly familiar and unspeakably strange. Tonight, as the world quiets and your mind slips toward the gentle twilight between waking and sleep, let us wander together into this mirror darkly, and let the enigma of antimatter unfold around us like the first notes of a symphony yet unheard. Imagine for a moment a world constructed not of the atoms you know, but of their ghostly counterparts, an entire reality made from the fleeting stuff of antimatter. The thought itself carries an allure, a sense of forbidden territory, as though one might slip through the looking glass and find oneself standing on the other side of the cosmic divide. Yet, in the world of popular culture, antimatter is often less a gentle muse and more a harbinger of explosive power and unfathomable mystery. Consider the starships of science fiction, their engines humming softly with the promise of impossible speed. In the universe of Star Trek, the warp drive sings its way through the interstellar night, propelled by the elegant annihilation of matter and antimatter. The ship's heart, the warp core, is envisioned as a containment chamber, its blue glow hinting at the titanic energies locked within, ready to be unleashed in the service of exploration and adventure. There is a poetic symmetry here, matter and antimatter, perfect opposites, meeting at last in a flash of light that sends the ship surging faster than the speed of light, beyond the reach of known physics and into the embrace of the unknown. Or let your mind drift to the cold stone corridors of Vatican City as rendered in Dan Brown's Angels and Demons. There, beneath the hallowed domes, a vial of antimatter glows with sinister promise, its potential for destruction held at bay only by the slenderest of magnetic fields. The tension is palpable, the stakes nothing less than the fate of a city or perhaps the world itself. Antimatter, in these stories, is both a tool and a terror, an energy source beyond imagining, and a weapon of almost mythic potency. But what truly is this substance that so fascinates and terrifies us? Let us step gently past the myths and the cinematic spectacle and peer into the subtle reality that lies beneath. In the language of physics, antimatter is the mirror image of matter, the same, yet opposite in a fundamental way. For every particle of ordinary matter, there exists a corresponding antiparticle. The electron, that tiny whirl of negative charge that orbits the nucleus of every atom, has its twin, the positron, identical in every way save for its positive charge. The proton, center of the atomic heart, is shadowed by the antiproton, and each neutron is balanced by its antineutron. This symmetry is not merely a poetic conceit, it is inscribed in the very equations that describe the universe, first glimpsed in the mathematics of Paul Dirac nearly a century ago. Dirac, with his wild hair and eyes alight with visions of the unseen, wrote equations that at first seemed to speak nonsense. They predicted not just the familiar electron, but another particle, one with the same mass, but the opposite charge. For a time, this was a curiosity, a mathematical ghost. But then, in 1932, the positron was discovered in the tracks of cosmic rays, and the world changed. Suddenly, the universe was doubled. Every particle had its antiparticle. Every act of creation bore its shadow. Yet the symmetry is not quite perfect, for if it were, we would not be here to marvel at it. The universe, as we know, is built of matter. The antimatter world, though not impossible, is elusive to the point of vanishing. And so, in science fiction, antimatter becomes a thing of wild power, rare, precious, and dangerous. It is the ultimate fuel, the ultimate weapon, the ultimate unknown. Let us linger for a moment on the image of the warp core humming in the heart of a starship. In the vision of Star Trek, matter and antimatter are brought together in controlled reactions, their mutual annihilation releasing pure energy in accordance with Einstein's famous equation E equals mc2. The numbers here are staggering. A single gram of antimatter, meeting its counterpart, would release energy equivalent to many thousands of tons of TNT, more than enough to hurl a ship across the stars or to vaporize a city. Yet even as we dream of such engines, the reality is more nuanced. To create antimatter is a feat of immense difficulty. In laboratories like CERN, deep beneath the fields of Switzerland, scientists labor to coax the briefest flickers of antimatter into existence. Protons are slammed into targets at near the speed of light, and in the firestorm of the collision, particles are torn from the fabric of the vacuum itself. Among the debris, for every countless millions of ordinary particles, a few precious antiparticles are born. They dance for an instant, then vanish, annihilated as soon as they meet the ever-present matter of our world. It is as if the universe itself conspires to keep antimatter at bay, to confine it to the margins of possibility. These facts do not diminish the romance of antimatter, but they do place its fictional portrayals in a new light. The Star Trek warp drive, with its casual containment of kilogram quantities of antimatter, is a vision far beyond our current reach. The energy required to produce even a milligram of antimatter is vast, and the technical challenge of storing it, keeping it from touching the walls of its container, lest it annihilate in a burst of radiation, is formidable. Electromagnetic traps, like invisible cages, are required to hold even the tiniest amounts. At CERN, a few thousand atoms of antihydrogen have been held for brief moments in such traps, their existence a testament to human ingenuity and patience. The antimatter bomb of Angels and Demons, too, is a fiction. The story tells of a 1/4 gram of antimatter, enough to level a city, concealed in a magnetic bottle. In reality, the world's total production of antimatter across decades amounts to less than a billionth of that amount. To gather even a milligram would take thousands of years at current rates, and the energy bill would beggar nations. Yet even as we smile at these exaggerations, we should not dismiss the kernel of truth that lies within them. Antimatter is, in theory, the most efficient energy source possible. When matter and antimatter meet, their entire mass is converted to energy. There is no waste, no ash, no lingering remnant. The fire that results is pure, absolute, and total. If we could produce and contain it in quantity, the implications for energy, propulsion, and perhaps even weaponry would be profound. The universe, it seems, has given us a glimpse of a power both beautiful and terrible, and then has hidden it away, just out of reach. But why is this so? Why, in a universe governed by symmetry, is antimatter so rare? Why do we not see stars and planets made of antimatter? Why do we not find great clouds of it drifting between the galaxies? The answer lies deeper in the story of the universe's birth, in the subtle breaking of symmetry that occurred in the first moments of time. But let us not hurry there. For now, let us linger in the half-light and contemplate the properties of antimatter itself. To understand the enigma, it is helpful to return to the notion of the cosmic mirror. Imagine two worlds, perfectly balanced, one of matter, one of antimatter. In every respect, they would appear identical, the same chemistry, the same physics, the same complexity of structure and life. Yet the two could never meet without disaster, for their contact would mean mutual annihilation. It is as if the universe is divided into two great provinces, each forbidden to the other, each a reflection of the same fundamental laws. This symmetry is not absolute, but it is profound. The interactions of particles and antiparticles are governed by the same rules, save for the reversal of certain charges and quantum numbers. If you were to shake hands with your own antiparticle, the moment of contact would be your last. Both of you would vanish in a burst of gamma rays, the energy of your mass transformed in an instant into light. There is a certain melancholy to this, a sense of lost possibility. Antimatter is not evil, nor is it forbidden, but it is forever opposed to the world we know. Its existence is a reminder that the universe is stranger than we can imagine, that the surface of things conceals depths yet unplumbed. The fact that we can create and study antimatter, even for the briefest of moments, is a testament to the reach of human curiosity. In the great accelerators of the world, beams of protons are spun to unimaginable speeds, smashed together in rings and tunnels that stretch for miles beneath the earth. The collisions are violent, but in the chaos, order emerges. New particles are born, some known, some never before seen. Among them, antimatter appears, as if conjured by the equations themselves, a fleeting visitor from the other side of the mirror. In the early days, this was a revelation. The tracks of positrons, curved in magnetic fields, revealed their presence unmistakably. The antiproton, heavier and more elusive, was found in the aftermath of ever more energetic collisions. Today, physicists at CERN and elsewhere work to create entire atoms of antimatter, antihydrogen, composed of a positron orbiting an antiproton. These atoms are trapped, studied, and compared to their matter counterparts, in the hope of finding some small difference, some crack in the mirror that might explain the imbalance of the cosmos. For now, though, the mirror holds. Antimatter behaves as theory predicts. Its properties a perfect echo of matter's own. The laws of physics, as far as we can see, are impartial, a fact that is both comforting and unsettling. As you drift deeper into the quiet, let your mind rest in this place of symmetry and enigma. Antimatter, so often depicted as a force of chaos, is in truth a thing of order, a necessary partner to the world we know. Its rarity is a mystery, its potential a source of both hope and caution. The stories we tell, of starships and bombs, of angels and demons, are reflections of our own fears and desires, projected onto the canvas of the unknown. Yet the true story of antimatter is only beginning. In laboratories around the world, experiments continue. The faint glow of trapped antiparticles, the whisper of annihilations counted in detectors, the equations scrawled on chalkboards late into the night, all speak of a quest unfinished, a mirror still to be fully understood. There are deeper mysteries yet to explore. Why, in the aftermath of the Big Bang, did matter come to dominate? What subtle laws or accidents tipped the balance, leaving the universe we see and not its perfect opposite? The answers lie ahead, in the dawn of time and the heart of the atom, where the enigma of antimatter awaits its next revelation. In the silent, secret theatre of the cosmos, shadows dance alongside every particle of light. For every familiar star, every stone, every cell in your body, there exists, or perhaps existed, a spectral counterpart. This counterpart is not merely an idea, but a real, tangible entity, born with the same mass, the same magnitude of charge, the same quantum numbers, but with a twist so subtle and so profound that it shapes the story of everything we know. This is the realm of antimatter, a world that is both our mirror and our mystery. To understand antimatter, let us first revisit the idea of symmetry, a notion that nature seems to cherish with almost mathematical devotion. In the language of physics, symmetry is not just beauty. It is a principle that governs the laws of reality. Imagine, if you will, holding a perfect crystal up to a mirror. The reflection is identical, yet reversed. A left becomes right, a right becomes left. In the mirror, your image raises its left hand when you raise your right. This is a simple form of symmetry, a spatial inversion. But in the quantum world, symmetries run deeper. There exist transformations more abstract than mere reflections: charge conjugation, which swaps positive for negative charges; parity, which flips spatial coordinates; and time reversal, which runs the universe backward. The interplay of these symmetries is woven into the very equations that describe particles and forces. In the early 20th century, physicists believed that the universe respected these symmetries perfectly. The rules that govern particles, they reasoned, must also apply to their mirrored, oppositely charged twins. Then in 1928, Paul Dirac, a man with the quiet demeanor of a dreamer and the mathematical sharpness of a blade, wrote an equation that would forever alter our conception of existence. Seeking to marry quantum mechanics with the theory of special relativity, Dirac's equation described electrons with uncanny precision. Yet hidden in its solutions were not only the familiar electrons with their negative charge, but also solutions that implied the existence of particles identical in every measurable way, except for their charge, a positive electron or positron, the first known antiparticle. This was no idle artifact of mathematics. In 1932, Carl Anderson, sifting through the cosmic rain of particles in a cloud chamber, glimpsed a track that bent the wrong way in a magnetic field, betraying a particle with the mass of an electron but a positive charge. The positron was real. It was as if a shadow, long suspected, had at last stepped into the light. Soon, physicists realized that every particle in the Standard Model, the electrons, the protons, the neutrons, the neutrinos, has its own antiparticle with the same mass, the same propensity to exist, but with its quantum properties, like electric charge and certain spin orientations, reversed. Yet here the symmetry falters, and the dance with shadows becomes strange. When a particle meets its antiparticle, the two do not simply coexist. Instead, they annihilate in a brief, spectacular flash, converting their mass into pure energy, often in the form of gamma rays. It is as if the universe, in its fundamental bookkeeping, cannot abide both matter and antimatter in the same place at the same time. Their encounter is not a gentle fusion, but a mutual erasure, a return to the primordial light from which both sprang. Despite their apparent symmetry, matter and antimatter are not found in equal measure. Peer into the depths of space, and everywhere you look, planets, stars, nebulae, all are built from matter. Antimatter, by contrast, is a rare visitor, fleeting and elusive, glimpsed only in the high-energy collisions of cosmic rays with the atmosphere, or conjured for a heartbeat in the magnetic traps of particle physicists. The observable universe is overwhelmingly made of matter. This is the puzzle of cosmic asymmetry, the great riddle of the missing antimatter. To appreciate the subtlety of this riddle, let us wander through the properties that distinguish matter from antimatter. Take the electron, a particle whose existence is woven into every atom, every chemical bond. Its antimatter twin, the positron, shares its mass, its spin, even its magnetic moment. Yet, the positron carries a positive charge, while the electron's is negative. When a positron and an electron meet, their charges cancel, and their combined mass is transformed into photons, particles of light. The same is true in principle for other pairs, the proton and the antiproton, the neutron and the antineutron, each with their charges and quantum numbers reversed. But nature is not always so neat. The neutron, for example, is electrically neutral, but its antiparticle, the antineutron, is distinguished by its internal structure, It's quarks replaced by antiquarks, their charges reversed in a deeper sense that is revealed only through their interactions with other particles. The neutrino, seemingly massless and without electric charge, has an antiparticle, the antineutrino, which is identical in almost every way, save for the orientation of certain quantum properties, such as lepton number. These distinctions are subtle, but their consequences are profound. If the universe began with equal amounts of matter and antimatter, as the laws of physics would seem to allow, then why does the night sky not blaze with the light of their annihilation? Why is our world not an ocean of photons, the aftermath of perfect mutual destruction? Here, the idea of symmetry meets its limits, and the universe reveals a preference, a faint but decisive tilt. In the aftermath of the Big Bang, as the seething soup of energy cooled and particles condensed from the void, matter and antimatter should have formed in equal numbers. Yet for reasons still not fully understood, a tiny excess of matter survived. For every billion pairs of matter and antimatter particles, there was one extra particle of matter. The rest annihilated, leaving behind the faint afterglow we now observe as the cosmic microwave background, the ghostly echo of creation itself. That single part in a billion became every atom in every star, every planet, every living thing. Physicists have searched for the cause of this imbalance, probing the boundaries of symmetry in nature. In the laboratory, they study violations of charge parity, CP symmetry, subtle effects in the decays of certain particles, such as neutral kaons and B mesons, where the behavior of matter and antimatter diverges ever so slightly. These violations are rare and minute, like a gentle current in the vast river of physical law, yet they hint at mechanisms that could, in the early universe, have tipped the balance toward matter. But the known sources of CP violation are too feeble to account for the observed abundance of matter. The gap between theory and reality remains, like a whispered secret in the halls of the universe. Some physicists speculate that unknown processes, perhaps involving neutrinos or hidden sectors of particles, may have driven the cosmic baryogenesis, the creation of the matter excess. Others seek answers in the symmetry-breaking transitions that marked the early moments of cosmic history, when the forces of nature themselves changed character. In the meantime, antimatter continues to tease and tantalize from the periphery of experience. In the depths of space, high-energy collisions between cosmic rays and interstellar gas produce fleeting showers of positrons and antiprotons. Here on Earth, particle accelerators like CERN's Large Hadron Collider smash protons together at near light speed, momentarily recreating the conditions of the early universe. In these violent encounters, particles and antiparticles spring into existence, dance their brief dance, and vanish in mutual annihilation. Even more delicately, physicists have learned to coax antimatter into traps, penning positrons and antiprotons in magnetic bottles, combining them to create antihydrogen, the antimatter mirror of the simplest atom. These anti-atoms are studied with exquisite care, their spectral lines measured and compared to those of ordinary hydrogen. So far, the symmetries hold. Antihydrogen appears to be a perfect reflection of hydrogen, at least to the limits of our measurements, yet the search continues for a crack in the mirror, a sign that the balance is not exact. The rarity of antimatter is not merely a cosmic curiosity, it is a practical challenge. When antimatter is created in the laboratory, it must be carefully contained, shielded from contact with ordinary matter. Even a grain of antimatter, if it touched the air, would release energy in an explosion more powerful than the most potent chemical bombs. For this reason, antimatter remains a precious commodity, measured in atoms and stored for fractions of a second. Yet nature finds ways to create antimatter in the wild. Thunderstorms, for instance, can hurl gamma rays skyward with enough energy to birth positrons. The heart of our galaxy, racked by violent processes near the central black hole, is a source of positron annihilation, as seen in the faint 511 keV gamma ray line observed by space telescopes. Even the radioactive decay of certain isotopes, such as potassium-40 in your own body, occasionally emits a positron, a reminder that the boundary between matter and antimatter is never absolute. But if antimatter is so rare, so fragile, where is it hiding? Could there be regions of the universe where antimatter reigns? Astronomers have searched for the telltale signs, the unique gamma rays produced when matter and antimatter meet. So far, they have found no evidence of entire stars, galaxies, or clusters composed of antimatter. The absence is striking. The universe, it seems, is a kingdom of matter, with antimatter exiled to its margins and memories. This cosmic imbalance raises questions that ripple through physics and philosophy alike. Why does the universe exist at all, rather than a featureless bath of light? Why are we here to ponder this question, built from matter and not its reflection? The laws of physics, with their elegant symmetries, seem to permit both possibilities, yet reality has chosen one over the other. In the laboratory, the pursuit of antimatter is both a technical marvel and a philosophical quest. The creation and containment of antihydrogen atoms, for example, is a feat that requires magnetic fields of exquisite precision, cryogenic temperatures near absolute zero, and detectors sensitive to the faintest whispers of annihilation. Each antiatom is a message from the mirror world, an invitation to ask whether the rules are truly the same on both sides. Researchers measure the spectra of antihydrogen, hoping to find a difference, a shift in the frequencies of its light, a sign that symmetry has been broken. They test whether antimatter falls in the same way as matter under gravity, a question so fundamental that its answer could shake the foundations of our understanding. So far, antimatter seems to obey the same laws, but the search for exceptions continues, ever more precise, ever more hopeful. In this dance with shadows, the universe keeps its secrets close. The symmetry between matter and antimatter is at once profound and incomplete. We have learned to conjure antimatter, to study its fleeting presence, to marvel at its power and promise. Yet the question of why the universe prefers matter, why the mirror was shattered in favor of one reflection, remains unanswered. Beyond the laboratory, the search widens. Astrophysicists scan the heavens for cosmic rays that might carry the signature of antimatter from distant reaches of space. They dream of finding an antinucleus, a fragment of antihelium, drifting from a distant antigalaxy. Such a discovery would rewrite our understanding of cosmic history, yet for now the evidence is silent. And so, as you drift into the quiet spaces between thoughts, imagine the universe as a grand ballroom where matter and antimatter were once partners in a perfect waltz. Somewhere the music changed and matter took the lead, casting antimatter into the shadows. The dance continues, unseen but not unfelt, in the rare flashes of annihilation, in the mysteries of cosmic origins, in the silent longing of symmetry for completion. Ahead, the story of antimatter is far from finished. The questions it raises reach into the heart of reality, promising new wonders to those who seek the hidden music of the universe, a music that beckons us onward into deeper mysteries yet to be revealed. Beneath the glimmering surface of things, in the world's hidden lattice, there are stories that flicker just beyond the edge of ordinary understanding. Antimatter, so often imagined as the stuff of science fiction, the ghostly double of all we know, has drawn human curiosity for nearly a century. Our efforts to glimpse and even grasp this ethereal twin have unfolded as a tapestry of theory and experiment, of wild imagination and patient craft, woven together by physicists determined to coax the unseen into the realm of the known. So let us drift back, quietly, to the early days of this quest, to to a time when the very notion of antimatter was itself a kind of mathematical whisper emerging from the chalk-dusted equations of a contemplative mind. The year is 1928. In a study cluttered with books and the faint scent of pipe smoke, the physicist Paul Dirac sits, lost in the beautiful wilderness of mathematics. Dirac is seeking to reconcile two pillars of physics, the quantum theory, which governs the subatomic, and Einstein's special relativity, which rules at speeds near that of light. What he creates is an equation, a subtle, elegant thing, that describes the electron, the familiar bearer of negative electric charge. But Dirac's equation is like a mirror, reflecting not just one world, but two. It suggests the existence of a particle identical to the electron in every respect, yet bearing a positive charge. At first, Dirac hesitates. He even imagines this mirror electron might be the proton, already known to science. But the masses do not match, and the mathematics is stubborn. Eventually, the only path is to accept the implication. Nature must allow for the existence of anti-electrons, particles with the same mass as electrons, but with opposite charge. Thus, the positron is born, not in the laboratory, but in the silent cathedral of mathematics. Skepticism greets this ghostly prediction. For a time, the positron is an idea without a body, a shadow without a source of light. Yet the universe is patient, and sometimes theory must wait for the world to catch up. That moment arrives in 1932, high in the mountains of California, where a young physicist named Carl Anderson bends over a cloud chamber, watching for the faint trails left by cosmic rays as they pass through a supersaturated vapor. The instrument is simplicity itself, a small box filled with alcohol vapor, cooled almost to freezing, where charged particles passing through leave visible streaks like airplane contrails in a miniature sky. On one particular photographic plate, Anderson sees something uncanny, a track that curves in the magnetic field just as an electron's would, but in the opposite direction. The trace is too light and too agile to be a proton. It is, unmistakably, a positively charged particle with the mass of an electron. The positron has materialized, summoned from the abstract realm of equations into the tangible world. In that moment, antimatter steps from the shadows, and the grand quest to capture it begins. This first encounter had the aura of serendipity, but it also marked a turning point. No longer merely mathematical, antimatter prompted new questions. Where does it come from? Why is it so rare? And most hauntingly, what happens when it meets its ordinary sibling? The answer to this last question, already hinted at in Dirac's theory, is both elegant and alarming. When a particle of matter and its antimatter twin touch, they annihilate, their mass transfigured into a burst of pure energy, gamma rays, with power far greater than that released in any chemical fire. Matter and antimatter, it seemed, could only coexist in the briefest of embraces, like dancers whose union is always a final waltz. If the positron was the first antimatter particle to be discovered, it would not be the last. In the years that followed, physicists uncovered the antiproton, the anti-neutron, and gradually built a mirror menagerie of antiparticles, each a shadowed counterpart to the familiar building blocks of atoms. Yet nature does not freely offer up these spectral creatures. In the universe we inhabit, antimatter is prodigiously rare, swiftly destroyed wherever it encounters the overwhelming abundance of matter. The cosmos, as it turns out, is a most inhospitable place for antimatter to linger. To study antimatter, scientists would need to become alchemists, forging these elusive particles in the crucible of technology. The birthplaces of modern antimatter are not mountaintop cloud chambers, but vast humming laboratories, cathedrals of steel and magnetism like CERN, the European Organization for Nuclear Research, where the boundaries between the natural and the possible are stretched to their utmost. Here, deep underground, particles are accelerated to nearly the speed of light, whipped around colossal rings that span kilometers, steered and focused by magnetic fields of exquisite precision. In these colliders, protons are smashed together with unimaginable violence. The energies unleashed are so great that, for the briefest flicker of time, the vacuum itself boils with possibility. Einstein's famous equation, E equals mc2, tells us that energy can be transmuted into mass, and so, in these titanic collisions, pairs of particles and antiparticles leap into existence. A proton and its antimatter twin, the antiproton, an electron and a positron, each born together like twins from the same cosmic egg, only to be torn apart by the inexorable fate that most will annihilate and vanish in a blink. But a few survive, slipping past the carnage, and it is these precious survivors that experimenters seek to snare. The challenge is immense. Antimatter, by its very nature, is allergic to matter. A single touch, a kiss upon the wall of a container, and it is gone, annihilated in a flash of gamma rays. To hold it, to study it, requires ingenuity bordering on the magical. Here, physicists turn to the subtle power of electromagnetic fields. Charged antiparticles, like positrons and antiprotons, can be corralled using devices called penning traps, a marriage of electric and magnetic fields that creates a kind of invisible bottle. Within these traps, antiparticles can be kept away from the material walls, suspended in a vacuum, their lifespans stretched from microseconds to days. It is a delicate balancing act, a perpetual dance to keep the ghosts aloft and untouched. The trapping of neutral antimatter, such as antihydrogen, the antimatter twin of hydrogen, is an even more exquisite feat. Hydrogen, as you may recall, is the simplest atom, a single proton orbited by a single electron. Its counterpart, antihydrogen, consists of an antiproton core orbited by a positron. But neutral atoms cannot be confined by electric fields alone. Instead, physicists must use magnetic fields, exploiting the tiny magnetic moments of the atoms themselves to create a kind of magnetic bottle. At CERN's antimatter factory, teams of researchers have learned to coax antiprotons and positrons together, cooling them to temperatures barely above absolute zero, and nudging them into forming antihydrogen atoms, fragile things, more ephemeral than snowflakes under a summer sun. And yet, with the right arrangement of magnetic fields, they can be trapped, held motionless for minutes, even hours. The triumph of creating and trapping antimatter, though, is merely the beginning. The true quest is to probe its properties, to compare it, particle by particle, with ordinary matter. Are the laws of physics, those deeply woven symmetries, truly blind to the difference between matter and antimatter? Or are there, hidden in the fabric of reality, tiny asymmetries, secret biases that might explain why our universe is made mostly of matter and not a perfect balance of both? To answer these questions, scientists perform experiments of breathtaking delicacy. Lasers, tuned to frequencies measured with a precision of many decimal places, are fired at trapped antihydrogen atoms, seeking to detect the faintest differences in their spectral lines compared to ordinary hydrogen. The frequency at which the lone positron orbits the antiproton, the energy required to flip its spin, each is measured, scrutinized for any deviation from expectation. Thus far, nature has revealed only near-perfect symmetry, but the search continues, for even the smallest crack in this mirror could illuminate the deepest mysteries of creation. There are, too, experiments that test the gravitational behavior of antimatter. Does antihydrogen fall down, just as hydrogen does, in Earth's gravity? Or might it fall up, repelled by the very mass of our planet? Ingenious devices, like the Alpha and G-bar experiments at CERN, drop clouds of anti-atoms and watch, with patient eyes, for the path they trace as gravity tugs them downward. Early results seem to confirm that antimatter succumbs to gravity just as its matter twin does, but the quest for certainty continues, each new refinement a step closer to understanding. Throughout these endeavours, the dangers of antimatter are ever present, not dramatic explosions, as Hollywood so often imagines, but the relentless difficulty of containment. A nanogram of antimatter, if it were to meet an equal measure of matter, would release as much energy as a ton of TNT. In practice, however, the quantities produced in laboratories are vanishingly small, a few thousand atoms at a time, each a treasure to be preserved and studied. The threat, such as it is, comes more from the technical challenge than from catastrophic release. Vacuum pumps must be flawless, magnetic fields must not waver, instruments must be insulated from the ceaseless jostling of the outside world. Even so, the task of storing antimatter is Sisyphean. Inevitably, some particles escape the trap, touch the walls, and vanish in a flash of gamma rays. These annihilations are detected with scintillators and photomultiplier tubes, which register each brief burst of light as a tiny, mournful tally of loss. Every experiment is a race against time, a delicate negotiation with the impermanence of the ghosts we seek to know. Yet for all the obstacles, the quest continues, driven by a simple, inexhaustible curiosity. The more we learn, the more the universe seems to hint at deeper questions. Why, if matter and antimatter are born together in equal measure, does the universe favour one over the other? Are there subtle laws, as yet unseen, that tip the scales? Or might there be realms far beyond our sight where antimatter is king and matter the rare and hunted twin? In the halls of laboratories and the silent depths of underground tunnels, scientists persist, their days and nights punctuated by the quiet hum of machines, the flashing of detectors, and the slow accumulation of data. The search for antimatter is not merely a technical pursuit, but a meditation on symmetry, on the nature of existence itself. To capture a ghost is to learn the language of absence, to find meaning in what so often slips away. And so, in these dim-lit chambers, where the air vibrates with the aftershocks of ancient collisions, the work goes on. The trapped anti-atoms, held fast by invisible fields, await their next interrogation. The laser beams, tuned and retuned, dance across the vacuum. The detectors, ever watchful, listen for the faintest echoes of annihilation. Each moment is a balance between hope and loss, between the fleeting and the eternal. As the night deepens and the world outside falls silent, the questions linger, unresolved. What more will the ghosts reveal, if only we can hold them just a little longer? What secrets lie hidden in the mirror's reflection, waiting for the patient eye and the steady hand? This, then, is the promise and the paradox of antimatter, always just out of reach, always drawing us onward, into the heart of mystery, where the known and the unknown meet in a dance as old as time. If you listen closely to the universe, so closely that you can almost hear the hush between the stars, the silent music woven between galaxies, you might sense an absence, a missing half, an echo of something that never quite was. For every particle of you, for every atom in the air you breathe and the cells that make your heart beat, there was once the potential for another, a mirror twin, an antimatter sibling. Yet you are here, and the world is here, and the cosmos is a tapestry of matter, not of its elusive reflection. In this shadowed silence lies one of the most profound mysteries in all of science. Why is there something instead of nothing? Why are we here at all? To reflect on antimatter is to gaze into a cosmic abyss, to contemplate not only the rules of physics, but the very conditions that allow experience, consciousness, and being. If the universe had been born with perfect symmetry between matter and antimatter, every spark of creation would have been matched by its own undoing. Each electron would have met its positron, each proton its antiproton, and in their joyful reunion they would have vanished in flashes of gamma light, leaving behind a cosmos bathed in high-energy radiation, but devoid of structure, of planets, of stars, of you and me. Yet this is not the universe we find ourselves in. Instead, we drift through a reality where matter vastly outnumbers antimatter. The ancient hydrogen in your veins, the carbon in your bones, the calcium in your teeth, all are survivors of a primordial battle, a war waged in the first microseconds after the Big Bang. The fact of our existence is the residue of that imbalance, a cosmic afterthought. To reflect on antimatter, therefore, is also to reflect on the slenderness of our own odds, the fragility of our being, and the strangeness of the laws that govern the world. The question of why the universe is made of matter, and not equal parts matter and antimatter, is called the baryon asymmetry problem. It is a puzzle so fundamental that it touches the roots of physics and philosophy alike. It asks, why did the universe prefer matter when the equations of physics, as we first understood them, seem to treat matter and antimatter as equals? Is this imbalance a mere accident, a fluke of cosmic dice, or is it the outcome of deep, hidden laws yet to be uncovered? Physicists have spent nearly a century chasing whispers of an answer. In the early days of quantum theory, the equations of Paul Dirac suggested a symmetry so elegant it seemed almost sacred, for every particle an antiparticle. Nature, it appeared, was a perfect mirror, but experiments soon betrayed this dream. In the aftermath of the Big Bang, for every billion pairs of matter and antimatter particles, there was one lone extra matter particle. It was this tiny excess, 1 in a billion, that survived the Great Annihilation, that went on to form all the stars, galaxies, and worlds. How did this happen? The laws of physics, as we now understand them, do allow for subtle imbalances. Certain processes, governed by the weak nuclear force, treat matter and antimatter just a bit differently, a phenomenon called CP violation. The C stands for charge conjugation, the operation that swaps particles for antiparticles. P stands for parity, the flipping of spatial orientation. In a perfectly symmetric universe, the laws of physics would be unchanged under these transformations. But experiments with particles called kaons, and later with B-mesons, showed that nature, at its most fundamental, has a slight preference, an almost imperceptible bias. The universe is not a perfect mirror, after all. Yet the degree of CP violation we have observed is woefully insufficient to explain the overwhelming dominance of matter. It is a clue, not an answer, a hint that there are deeper, undiscovered principles at play. Some theories propose new particles or forces, others invoke the behavior of neutrinos, those ghostly messengers that barely interact with the world. The search continues as physicists probe the boundaries of the standard model, driven by the knowledge that our very being depends on the outcome. To reflect on this is to stand at the threshold of the known and peer into the abyss of the unknown. Antimatter is not just a curiosity, not merely the stuff of science fiction or the subject of arcane laboratory experiments. It is a question etched into the fabric of reality, a riddle that whispers of other worlds, other possibilities. What if the universe had tipped the other way? What if, in some alternate reality, antimatter won the primordial contest, and we were its ghostly shadow? To imagine such a universe is to realize how contingent, how precarious our existence is. The laws of physics are not written for our benefit. They are impartial, indifferent, and yet here we are, conscious beings able to ask questions, to puzzle at our own origins. The rarity of antimatter is not just a technical detail, it is the precondition for everything we hold dear. Without it, there would be no atoms, no chemistry, no life. The very asymmetry that seems so unjust, so arbitrary, is the wellspring of all beauty, all complexity, all meaning. Yet antimatter is not entirely absent. It lingers at the edges of the ordinary, manifesting in fleeting moments and rare events. In the radioactive decay of certain isotopes, a positron is born, living for a brief instant before it meets an electron and vanishes in a burst of annihilation. In the depths of space, high-energy processes forge antiprotons and positrons, which journey through the cosmos until they are swallowed by matter and erased from sight. In the heart of our machines, particle accelerators, PET scanners, antimatter flickers into being, a reminder that the mirror is never truly shattered. There is a poetic irony here. The stuff that could have unmade the universe, the agent of annihilation, is now harnessed for healing. Positron emission tomography allows us to peer inside the living brain, to diagnose illness, to save lives. In the hands of physicists, antimatter is not a threat, but a tool, a probe for exploring the deepest laws. Each time a positron meets an electron in a medical scanner, it is a tiny reenactment of the primordial drama, a faint echo of that ancient cosmic duel. But the study of antimatter is not merely practical. It is also an act of wonder, a meditation on symmetry and its breaking, on the strange beauty of imperfection. In mathematics and art, symmetry is often prized as the highest form of order, the hallmark of perfection. Yet in the universe it is the breaking of symmetry that gives rise to structure, to diversity, to possibility. The slight imbalance, the almost accidental excess, is what made everything possible. This realization leads us to a deeper question. Is the universe inherently lawful, or is it, at its heart, ruled by chance? Are the laws that favor matter over antimatter rooted in necessity, or are they the outcome of cosmic happenstance, a roll of the quantum dice? If the latter, then our existence is an accident of the highest order, a fluke so improbable that it borders on too miraculous. If the former, then the universe is a place of hidden order, waiting to be uncovered by minds bold enough to seek it. The edge of this mystery is sharp and glittering. It is here that science meets philosophy, and the questions become not just technical, but existential. What does it mean to exist in a universe that could so easily have been empty? What does it mean to be a thinking, feeling being in a reality where the laws are so finely tuned that the difference between being and nothingness rests on a 1 in a billion imbalance? Perhaps, as we reflect on antimatter, we are called to humility. The cosmos is vast and ancient, indifferent to our desires, and yet it is also comprehensible, at least in part. We are creatures of matter, born from the ashes of stars, shaped by the asymmetries of the early universe. Our very thoughts, our loves and dreams, are made possible by the same laws that govern the dance of particles and antiparticles. To study antimatter is to study ourselves, to trace the lineage of our atoms back to the first moments of time, yet the mystery persists. The search for the origin of matter's dominance drives some of the most ambitious experiments in physics. Deep underground, in caverns shielded from cosmic rays, detectors watch for the rarest of events: the possible transformation of a neutron into an antineutron, the decay of a proton, the subtle oscillations of neutrinos. In the vacuum chambers of accelerators, beams of particles and antiparticles collide at near-light speed as scientists search for new sources of asymmetry, new cracks in nature's mirror. Each experiment is a question posed to the universe. What are you made of? Why did you choose this path and not another? The answers may be slow in coming, or they may elude us altogether, but the act of asking, the relentless curiosity, is itself a kind of meaning. We are the universe pondering itself, matter grown conscious, seeking to understand why it exists at all. There is, in the end, a kind of poetry to this quest. The abyss is not merely emptiness, it is a space of potential, of possibility. Antimatter, though rare, is not gone. It is only hidden, waiting to be understood. Its study may hold the key to new technologies, new sources of energy, or even new ways of thinking about reality. Some dream of harnessing antimatter to power starships, to unlock the secrets of gravity, to open new windows onto the multiverse. Others see in it a metaphor for the human condition, the tension between what is and what might have been, between being and non-being. As we contemplate antimatter, we glimpse the strangeness at the heart of things. We are reminded that the universe is not only stranger than we imagine, but perhaps stranger than we can imagine. The laws that gave rise to matter's triumph are subtle and profound. They hint at deeper symmetries, hidden patterns, and the possibility of worlds beyond our own. To study antimatter is to press our faces against the glass of reality and peer into the dark, searching for our own reflection. And so, as the stars wheel overhead and the universe continues its silent expansion, we find ourselves poised on the edge of understanding. The abyss is not only a void, but a mirror, one that reflects our deepest questions back to us. In the shimmering absence of antimatter, in the faint afterglow of creation, we sense both the fragility and the wonder of our existence. The story is not yet finished. The darkness between the stars holds secrets still, and the quiet music of the cosmos plays on, inviting us to listen, to dream, and to seek. As our journey through the shimmering veils of antimatter drifts to a close, we watch its elusive particles twinkle like distant stars, fading into the hush of space. May this quiet wonder settle gently in your mind, inviting peaceful contemplation until we meet again beneath the cosmic canopy for more Dreamtime tales.